would be able to see because his index of refraction would be equal to 1.
Yeah, I guess so. This one isn't really clear to me. You got the answers, huh? We'll have to figure it out. Okay.
So does that have to do with how it would enter the eye?
Yeah, I guess so. Yeah, that sounds like it's on the right track.
So the theta from before it enters the eye and when it enters the eye would be the same, because it's the same index of refraction.
Okay, right,
So that means that it doesn't bend,
right.
and so then maybe it doesn't hit the retina.
Okay,
Meaning what? That's why he wouldn't be able to see.
let's see. So let's see your picture.
Well, I just have. I'm saying this is the normal.
Mm-hmm.
This is air, and then this is seen as air too, because
Right.
And then light enters.
Mm-hmm. Why don't you first draw what would happen in the normal eye? Or for comparison, let's draw what would happen in the normal eye. That's always a good test-taking technique anyway, to draw the two things for comparison. Good.
And so if this is the normal, or this is the normal, this would be theta 1.
Right. Now that actually won't quite work because after all, the normal is at an angle here, right? I guess you're, yeah, the normal is actually, so we always pretend that we bend at the midpoint, but actually it bends twice. It bends once at the first curved surface, and it bends again at the second curved surface. It's just a trick to pretend it bends at the normal here. It would be too complicated to draw the normals here. But yeah, it sounds like you're on the right track. So the point here is, in the normal eye, vision works correctly when light rays converge on the retina. That means in order for this to work correctly, the lens has to bend the light rays so they converge on the retina. That means the angle they come in at can't be the same as the angle that they're transmitted at. Otherwise, they're not bending.
Right.
All right, so is this lens going to bend the light?
No.
Because it's got the same index of refraction on the inside and the outside. Well, by Snell's law, we actually talked about this exact case, I think, maybe. We talked about if n2 is equal to n1, then theta 1 has to equal theta 2, which just means that it's not bending. Now, it would actually be too complicated to try to draw theta 1 and theta 2 here, because really the normals are perpendicular to these curved surfaces. You're really bending twice. But all we have to say is the light is not bending.
Yeah.
It's just going to go straight through. We don't need to, you only need to figure out what the angle is if the angle is going to change. If you know the angle is not going to change, we just know that however the light comes in, it's not going to bend. So the light is just going to go like this. And so it certainly does not seem like it's going to focus here. I guess maybe though you could wear glasses, and the glasses could converge the light for you. However, then they would only work for one distance.
Right.
You'd have to have a ton of different glasses in your pocket that you're constantly changing for a bunch of different distances, because normally the way you can see at different distances is that the lens of your eye adjusts,
Right.
but the lens of your eye is useless here. Okay, so I think you basically had that figured out. The purpose of the lens of the eye is to bend the light, but without a different index of refraction than the surrounding medium, you wouldn't bend the light. One other thing they might be going for here, to get a full explanation, do you remember the lens maker's equation? We talked about that. I think this is in the, yeah, this is on the front page, so it looks like he wants you to know how to use this. So this is the lens maker's equation. I don't know if you had a chance to do any examples with this, but anyway, what would that happen to the lens maker's equation here for this problem? So for this problem, what would n be?
1.
Yeah, this would be 1.
So now it becomes 0.
So what does that tell us?
That there's no focal length.
Take your time a little bit more. What does that tell us about the focal length?
1 over 0. Sorry.
Yeah, what is 1 over 0?
0. Or undefined.
It's kind of undefined, but this means that f is infinite, right? If we put something infinite down here, we would get a 0. This is worth going over because we've actually done a lot of cases with infinites. So we need to know that you can get a 0 if, in a division if you put infinity on the bottom. So this is telling us that the focal length here would be infinite. All right, so this is telling us that we have a lens with an infinite focal length. Does that actually help us to explain this here? So if the, all right, and then you could say, well, an infinite focal length is like a plane mirror, right? Which means it doesn't bend the light.
Right.
This is just another way of showing it's not going to bend the light. Something with an infinite focal length is basically like something that was flat. This isn't flat, but it's going to behave as if it was flat. Basically, this is going to, remember that we can think of f as a measure of flatness. Here, even though this is not flat, it behaves as if it was flat because it's not bending the light. Well, again, something that was flat would not have any converging power. All right, so that actually might be a good part of the explanation since he included that in the front chart. We can actually build n right in here, but actually maybe your explanation at the beginning was just as well. This just really hits it. The thing that puzzles me is I don't see why you would be invisible if you have the same index of refraction as the air, because here's the person. So we know that some of the light is just going to pass right through the person without bending, but there's still going to be light reflecting. The way you see people is by the reflected light. So it seems like I don't see why you couldn't still see the light that's reflecting off the person over here. So I don't understand how he made himself invisible here. All right, so it was really pointless because he made himself invisible and he couldn't see. So, all right, so no wonder he was so crabby. All right. I must be missing something there. I'm sure H.G. Wells knows more optics than I do. Okay.